So dear students, today we are continuing our chapter Oscillations, in which we will take here the topic displacement first. What do you mean by displacement concerned to oscillations? It can be properly understood that if we take different examples of the displacement variable, suppose first example is for an oscillating pendulum, an angle from vertical as a function of time is a displacement variable. Similarly, we can take here another example to properly understand what is the displacement. In an AC circuit, the voltage across a capacitor as a function of time is also a displacement variable. Remember that this displacement variable may be positive or negative. Now if we go for a mathematical expression for the displacement concerned with the oscillatory motion, displacement variable, say if a function in time is given as a cos omega t, where a is the amplitude, cos omega t a function with respect to time, a variant function, time variant function. Similarly, we can consider another example of time variant function as ft equals to a sin omega t plus b cos omega t, where both sin omega t and cos omega t are the time variant functions, and for this function we can consider here the resultant amplitude as square root of amplitudes a square plus b square. And if we take here the phase angle, the initial phase angle for this time variant function, we can give it as phi equals to tan inverse b upon a. Now we will discuss a part, or you can consider a type of a oscillatory motion known as the simple harmonic motion. A simple harmonic motion SHM is an oscillatory motion, is the simplest form of an oscillatory motion in which the force on oscillatory body is directly proportional to the displacement of body with respect to its mean position. To understand the simple harmonic motion properly, we can consider here an example. Say a particle is vibrating back and forth about the origin of a y-axis between the limits of its maximum displacements plus a. See in the given diagram, suppose an object is here at the position of coordinate 0 0, or you can say the position of origin at O. Here we are considering that this object or the particle which is at rest at initial position O, and it starts to move towards positive y-axis up to the maximum displacement plus a, and again comes back towards its mean position or starting position, but cross this position after some time and move to the maximum displacement in the negative y direction, and again moves towards its mean position. So in a complete cycle of its motion from starting from O and reaching at O again, it takes two displacements each in positive and negative y-axis direction. Now if we record its displacement with respect to time from its mean position, the curve you have been seen here in the green line will be traced. So when we record the position of particle with respect to time, the displacement of the particle, the moving particle, will be given here by the expression y, which is the function of time, as a sine omega t, where a is the amplitude, the maximum amplitude, and omega is the angular frequency for the oscillatory motion of that particle. Thus, in this case, a periodic motion is a sinusoidal function of time. If the initial phase of displacement equation be phi, yt will be given by a cos omega t plus phi, and here we can trace the curve. The value of phi It will depend on the displacement and velocity of the particle at the time instant t equals to 0. The phi depends on displacement and velocity of particle at initial time, that is t equals to 0. So today we have discussed how the simple harmonic motion is produced by the motion of a particle. We will continue this chapter next one. Till then, good day.